Hi everyone, welcome to lecture 11 of 188. Let's start with a couple of announcements. Project 2 was due last week, Friday, but there's a mini contest that's optional in which you get to compete with other agents, staff agents, and in the future other student agents. On a board where on one side you are Ghost, you're supposed to defend your territory, and the other side you're Pac-Man, supposed to go eat the food pellets and bring them back. But if the Ghost catch you on the other side before you bring them back, then you explode back into food pellets and you get reset. So this optional contest ends on Sunday. Currently on the leaderboard, at number 1 we have YZS. It's YZS here, right there. Congratulations. At number 2, we have Team No Bug. Are they here? Team No Bug over there. Congratulations. And at number 3, we have Yu Chen Wu over here. Congratulations. So we have till Sunday for this contest, and we'll round up results of the final leaderboard likely next week. You can get extra credit by being near the top of the leaderboard, or also by beating staff agents. So independent of what the other students do, if you beat enough staff agents, there's also extra credit for that, 0.5 points for every staff agent you beat sufficiently often. So that's with a Sunday timeline. Homework 5 was released and is due on Monday. As usual, it has 3 components. There is the electronic part, there's the written part, and then there is a self-assessment of the previous written as part of the homework. Project 3, Reinforcement Learning, is also released, and it's due next week, Friday at 4 p.m. Any questions about logistics? Okay, let's dive into the technical contents then. This is our second lecture on reinforcement learning. Just as a reminder, what's going on in reinforcement learning? We will still assume there's a mark of decision process. What does that mean? That there's a set of states, a set of actions, which might depend what's available on which state you're in. There is an underlying model that says, what is the probability of landing in state S prime if you were in state S and took action A? And there's a reward function that tells you, if you were in state S, took action A, landed in S prime, how much reward did you get? Or will you get when it happens again? And what we're looking for is a policy pi of S that tells us for every state what is the best thing to do, where best is defined as maximizing expected discounted sum of future rewards. The twist in reinforcement learning is that we don't know T or R, so we have to experiment in the world to figure out how it works, how the transitions are, and where the reward is, to then from that maybe figure out how we can then optimize how much reward we collect. The big idea we covered last time is that you can compute averages instead of having access to T, and we'll review some of that now. Big picture-wise, with mark of decision processes and reinforcement learning, a total of 4 lectures. What have we seen? In the first 2 lectures, the MDP was known. There were 2 types of techniques we looked at. We looked at computing optimal value V star, optimal Q value Q star, optimal policy pi star. We had 2 algorithms for that, policy iteration and value iteration. They assume access to the model and to the reward function. And then we also saw you can evaluate a policy. So somebody fixes a policy, you can evaluate it, see what the value is, and that's called policy evaluation, which you could do in 2 ways. It turns out you could do it just like value iteration, but instead of having a max over actions, the action is fixed to whatever the policy prescribes. And so it's like being in a new MDP where only 1 action is available in every state, and it's running value iteration, that new MDP, it's a very simple MDP where the action is fixed for every state. That's policy evaluation. One way to do it. The other thing that happened is once we got rid of that max in the value iteration equation, it becomes a linear equation. So we could also just solve a linear system of equations to find the values of a policy. That's when we know the model and we know the reward function. Then, last lecture, we started looking at what if we don't know the model and or the reward function. And we saw there's two ways of tackling this. The model-based approach is one where we say, okay, let's collect data. From that data, estimate T and R, and then we can reuse the techniques we already know. And that's model-based reinforcement learning. So that's one way to do it. Another way to do it is to say, well, actually, rather than learning the models, we can directly learn values, Q-functions, policies. We saw this in two ways. We saw first value learning. Under value learning, we saw two approaches. We saw direct evaluation, where we just look from a state every time we were there, how much reward did we get in the future, and average it. And we saw temporal difference learning, or indirect evaluation, where we use the Bellman equation, but a sampled version to, from every experience, update our estimate of the value of the state we were just in. And we saw then that we can also do this with Q values, and that has a lot of benefits, because if you do it with Q values, it also tells us what action to take in any given state. So that's what we'll look at more today, and expand on what we covered there. So in model-free learning, what we have is effectively a stream of experience, and from that stream of experience, we want to somehow learn something. And we want to do it whenever there is a transition, an entity of this type, so one part of that stream, we want to update what we know so far. And the way we've done it is by mimicking the Bellman equation, but doing it in a sample-based way rather than requiring access to the model. So let's take a look again at how that worked. This is the Bellman equation for Q values. What did it say? It says the value for being in state S and taking action A, if we have k plus 1 steps yet to live in the life of the agent, is equal to a sum over states that we might land in, and it's a weighted sum based on the probability of landing in that state. The reward we get for that transition plus a discount factor gamma times what we expect to get in the future. And in the future, there's only k steps left now, so this is qk. We start from q0 equals 0 and can work our way up to any k going up one at a time. Why a max here? Well, we're trying to compute the optimal q values, and so when we think about what is the value from the current state in action, it's the reward we got instantaneously, plus what we expect to get if we act optimally from then onwards. And optimally from then onwards means that we need to take the optimal action over all choices of action available at that next state S prime. Of course, now we wanted to compute this without knowing T and R. And T and R are featured quite prominently in here. So, what we do is we experience a transition, S, A, R, S prime. What that gives us is, in some sense, the ability to compute one such term in this weighted sum. So, this is our sample estimate based on just one of these terms. Of course, we don't want to just say that the Q value for state S action A is equal to this, because there could be many future states S prime, and this is just one that we experience out of many possible future states S prime. So we're going to do an averaging over the many times we were in state S and took action A. What was the sample estimate of the value? So the way we average is with a running average, so we don't have to keep everything around. We say, okay, our current running average is QSA. We have a new sample estimate, this one over here. We're going to average them together in a weighted way. If alpha is 1/2, then we have 1/2 what we used to have, 1/2 the new sample estimate. In practice, alpha will be much smaller than 1/2. So the sample update, the update here will be dominated by this term over here, but a little bit of an adjustment based on this term here. Any questions about this? Because this will be the foundation for the first half of lecture today. Yes?
Why do we pick alpha if we just have it evenly, have even contribution rather than alpha?
Okay, it's a good question. So you could say, well, in some sense the question is, how do we even choose alpha? If alpha is fixed, then what we get is the latest ones contribute more than the early ones because they get downweighted over time. So you could think of it as a feature or as a bug. Let's think about this. Well, if the later ones get more weight in the result than the earlier ones, the reason we might like that is because as we've been doing this for a while, the Q values become more and more accurate. And as the Q values become more accurate, then the sample estimate that we compute here will be a more accurate one than the one we had before. And so the later experiences result in sample estimates that are more accurate than the early experiences. And so that's why we actually consider it a good thing that the later ones contribute more than the earlier ones. But in principle, if you wanted them all to contribute equally, you could probably find a calculation to do that. In practice, we don't care about that. We'd rather have the later ones contribute more. And it happens to also be very convenient, because then we can do this exponential weighted average for which we don't need to keep as much information around. Any other questions? Okay, let's build on this then. What are some of the properties? The update equation we just looked at, if we use it often enough, meaning we collect enough experience, the Q values will converge to the optimal Q values, even if you're acting suboptimally. And this is very surprising, because typically when you try to compute values, like we saw in the standard value evaluation type setup, you would compute the value of the current policy. But with this update equation, and this is because of the max that's happening in here, that max makes it that the samples are referencing the optimal policy, even if the way you collect your data is not optimally. In fact, it'd never be optimal initially, because you don't know how to do things optimally. And so this is off-policy learning. That max in there enables off-policy learning, allows us to use any policy to collect data. Not any, there are a few caveats that we'll look at, but any policy that visits every state action pair sufficiently often is okay, and will result in the optimal Q values. What are these caveats? Caveats are you have to explore enough, more about that later, but one way to think of it is you need to somehow satisfy the condition that every state action pair is visited infinitely often. Your alpha has to go down, otherwise you don't get convergence, because the updates remain too big over time, so gradually decaying your alpha. But don't decay too quickly, because if you decay too quickly, you've only averaged a small amount of experience together, and it won't have converged yet to the right average. In the limit, it doesn't matter how you select actions, as long as these things are satisfied. So let's look at a demo to remind us of how this works. So here we're going to watch a Q-Learning agent, the presence of which you can see with the blue dot, and it's going to run on its own. So I'm not moving it around to let it run faster. It's going to run on its own. And it's running in this grid world, which happens to have a bunch of terminal states at the bottom, also terminal state all the way at the right. That's actually a good one. The bottom line is actually pretty bad to be at. I believe it's a negative 100 reward when you end up exiting from there. And the policy we see run here is a non-optimal policy, often jumps off the cliff. And the things to pay attention to here is that if you look on the optimal path, indeed it's converging onto a value of roughly 10, which is the optimal value of the discount factor is 1. You can also see that even when it jumps off the cliff, it retains the optimal values because it knows that that was not the optimal action. The update happens based on the max of Q values, not based on the action you actually took. And so jumping off the cliff does not affect the values that get propagated back, except, of course, for the action from where you actually do the jumping off the cliff, from which it's irreversible, where it has to affect all the downward actions from the middle row. There are some places it's barely ever been. That's something we'll address. I mean, in principle, there might be something really good there that it hasn't found out about yet, because it hasn't explored very fully. But overall, after a while, it converges to roughly the right values in the places, at least in the middle and the bottom, and this is happening despite acting fairly randomly. So the notion of needing to visit every state action pair sufficiently often is actually a tricky one, because it requires that you somehow understand where you've been, where you've not been, and somehow make sure that you are there in all places often enough. Simple example would be in real world, let's say you have your usual place to go for lunch, and it's pretty good, so you're pretty happy every time you go there. But then a new place has its grand opening, and now you have to make a decision. Are you going to try it out? It's risky. It's probably worse, because you're so happy with your usual lunch place. But if you don't try it, you'll never know. And so if you want to make sure you have the optimal policy, you have to go try this new place. If it's bad, you might never go back, but then maybe it's a good place, and it's more optimal, and you keep going there. But without trying, you won't know. And that's a critical aspect of exploration. You'll have to try things, and many of them that you'll try will actually not be good for you, but you didn't know ahead of time. You had to try it to find out. So what's a very simple scheme for exploration? Something called Epsilon greedy. It's very simple and actually used surprisingly often. Every time step, your agent will flip a coin. And with some small probability epsilon, so the coin is biased, and with a small probability epsilon comes up one way, probability 1 minus epsilon comes up the other way. Probability epsilon, it'll act randomly. Probability 1 minus epsilon, it'll look at the current Q values, look at which action is optimal based on the current estimates of the Q values, take that action. So this introduces randomness while usually playing according to the strategy that you think is best. And so what does this do? Well, it ensures that while you're learning, you usually do pretty good things, which you might want, so you're not just always acting randomly. But it also ensures that you have randomness in there, and if you run this long enough, every state action pair will be visited sufficiently often, and you will have your Q values converge to the optimal Q values. Let's take a look at this in action on the crawler. So what are we going to watch here? We're going to have the crawler robot again. You're going to work with that robot in your project 3. Now, this interface here will start making more sense. What do we have here? We have an explicit epsilon. It's right now 0.8. That's actually pretty high. That means that with probability 0.8, actions are taken randomly. Probability 0.2, the current Q function estimate is followed. There's a discount factor, there's a learning rate, and then there is some things we can use to accelerate the learning, meaning we can not watch everything live, but let it behind the scenes collect a lot more experience. So let's take a look at this up and running with epsilon equals 0.8. So this thing is acting mostly randomly at this point, so it's not really going anywhere. But we also know that's kind of okay. We know to learn good Q values, we don't need to act according to any optimal policy, as long as we get good coverage. And so if we see this thing get good coverage, we can expect it to learn a good policy. Now, we skip forward 30,000 steps, so it's collected even more experience. Skip forward 1 million steps. Now, through these random actions, it's seen pretty much everything. But if we look at it, it's still not acting that great. Why is that? It's actually learned the optimal Q values, but it's still using an epsilon that's 0.8. And so most of the time, it's not using those Q values to decide what to do. And so it's still behaving fairly poorly. But it's actually learned things underneath. I mean, we can't know that from just what we've seen so far, but we can hope for that. And soon we will decay, make epsilon smaller, and see that indeed, when it starts listening to its Q values, it's going to do really, really well. But as long as epsilon's large, it's never going to work all that well. But it's learning. It's doing a little better than initially with this large epsilon. But to really see what it's learned, we've got to start decaying epsilon. So let's decay epsilon, bring it down to maybe 0.0 or even 0 completely. Pure exploitation, no randomness anymore, and it's steadily making progress. So now we can see what it learned. And that's something you can in general do with your Q-Learning agent, periodically switch to a Q that is an epsilon that is 0 to see what it's learned so far. Okay, so this worked. Eventually, after we skipped forward many, many, many episodes, we had to lower epsilon over time to make sure we see better behavior. So that's something we need to keep in mind if we actually want to get good behavior out. But we didn't have anything automatic. And what we're going to look at now is something called exploration functions that will help us decay the exploration automatically based on how much you have already learned. Once you've learned a lot, you should maybe explore less. Okay, so we want to explore. Random actions are good in some sense, but they explore a fixed amount. A better idea is to pay attention to the parts of the space where you don't know much yet. If you don't know much yet, you should try things out you haven't seen yet. But if you already know how things work, there's no reason to, again, do random things. Okay, so initially, you don't know, you need to go check it out. But then once you've been there, you don't want to keep randomly checking it out. What we're going to use is something called an exploration function. Let me say something about that. F here is a function that combines two things. An estimate of what will be a utility, U, and then takes in also a count. So for each state action combination, we will keep track of a utility and a count. And rather than just choosing an action based on its expected utility, we'll choose an action based on expected utility plus this correction. This correction, k is a constant. Let's say maybe it's 10, who knows, some number. N is how often we've seen that state action pair. Maybe we'll want to n plus 1 here just to make sure that when we're at 0, it doesn't divide up to infinity. But so what happens here is when you've been somewhere only 0 times, this will be k. Once you've been somewhere 2 times, it will be k over 2. Once you've been somewhere 100 times, it will be k over 100. And so the more often you've been somewhere, the lower the second quantity becomes. And so the less you add to how you perceive the utility of exercising that state action pair. So what would it mean? Regular Q updates look like this, and this is a shorthand notation for a weighted update. We already have an estimate of Q. We're going to have a new sample estimate of Q, and we're going to combine it, 1 minus alpha the old thing plus alpha the new thing. That's what this means. We're going to replace this now. Instead of using this over here, we're going to correct it. So we're going to look for all actions that are available in state S prime. We're going to look at the Q value associated with action A prime in state S prime, but also look at how often have we been in state S prime and taken action A prime. And this thing here will be computed, which will give a bonus to actions that haven't been taken very often yet in that state. So now we're going to be favoring actions we haven't taken very often yet. What does it actually mean to favor these actions? What it means is that when we compute the sample estimate in this calculation over here, we'll end up with higher values. So what that really means is that if we're looking at the value of state S in action A, and we wonder how much is this really worth to take action A in state S, it'll say, well, that depends on whether in state S prime there are high Q values, but also in state S prime, are there actions available we haven't taken very often yet? And if there are actions available in S prime that you haven't taken very often yet, and you can reach S prime from taking action A in state S, then that will start favoring that action A in state S. So you're kind of thinking ahead here with this update. You're saying, how good is my action? Not just in terms of reward I'm going to get, but in terms of landing in a state S prime where there are actions available I have not explored much yet. And this will, of course, propagate back to the next one, and what will build up over time is Q values. They're not the actual Q values initially, but that estimate whether a certain action gives you exploration potential. And if an action has high exploration potential, you're more likely to take it. And so what that means is if you have a complicated environment, or maybe you need to run down a very long hallway, and behind that hallway there's a huge room with a lot of things to explore, then this thing will encourage you to go down that hallway until you've explored everything in that room. And once you have explored everything in that room sufficiently often, then these bonuses will start to decay, because the counts will be high, and the bonus is based on 1 over the count. These bonuses will start to decay you'll stop visiting that room, or maybe, if there's actually real value in that room, thanks to high Q values there, you'll still keep going there and go collect rewards. So it's a much more structured way of doing exploration than just in the moment picking something random. Any questions about this? Yes?
If you went down a hallway, wouldn't your end updates keep track of the fact that you've been down the hallway multiple times and no longer treat it as a place to explore, even though you might not have seen everything in the room at the end?
So let's say we have a hallway, bunch of states, and then here we have a massive room, and maybe here we have a hallway going another way, but only a small room. If we run standard Epsilon greedy-based exploration, and let's say we start out here, we'll end up spending less than half of our time in this room and more than half our time on this side. That's not good. We don't get a whole lot. Now your question is, why do we do better with this approach? Is it really true that we're doing better with this approach? Let's think about this. So let's say we go down this hallway. First time we go down, what will happen is, based on novelty, there will be updates to the states before, because we had actions available in the next state that make that state look good. These updates, based on high exploration bonus, because n is still low, will initially favor all states here. Then your question is, after you've been down that hallway many, many times, what will happen? What will happen is they will still be high because you'll still experience new things somewhere in this room, and they will backpropagate through these updates into the states in the hallway. Until at some point, there is no bonus anymore to be collected from this big room, at which point these Q values will start dropping down because there will be no contributions anymore from the exploration bonus. So the main point here is that even if exploration bonuses might not be that high anymore intrinsically in the moment, if you just think of them as rewards, because they propagate in the Q values, you'll still continue to favor going down that hallway. Any other questions about this? Okay, let's take a look at crawler with a exploration function. So this same setup as before. Epsilon is still 0.1 to ensure that there's at least initially a little bit of randomness, because if epsilon is 0 initially, then you already have a deterministic policy, and you're not going to see multiple things to see that there are exploration bonuses. So your epsilon is non-zero, but pretty small, so your behavior will be dominated by the Q function. With an exploration function, what that means, it will be dominated by a combination of how novel are the things available to me after I take this action, and how much reward is available to me after I take this action. Let's run this. This time, we're not going to jump forward by skipping 30,000 steps or 1,000,000 steps. We're just letting it run live. And so we're going to actually, in just about 10-20 seconds, see this thing learn to do things. Right now, there's still a lot of exploration, still a lot of things it hasn't tried. And so it's doing a lot of things to learn more. But then at some point, the exploration bonus starts to decay because you've seen things before, you've tried them before. Then that propagates into Q values, which then become dominated by actual reward, and it starts exploiting. And so here, we got something in just order of a few hundred or thousand steps, rather than needing to skip forward 1,000,000 steps before we get good behavior. Okay, so that's Q-learning with exploration. There's some other concept that's good to be aware of. It's called regret. It's a term that you know in real life. It's when you do something and you wish you hadn't done it. Maybe some people are thinking about that right now in Washington. Not sure. So there is a notion in AI also about regret, and it's actually quite related to the real-life notion, at least the one of wishing you hadn't done something you did. More formally, when we have an algorithm, we could try to compare them just based on do they get to an optimal policy, or we could compare them based on how quickly do they achieve an optimal policy. For example, we know epsilon greedy Q-learning and exploration function Q-learning both ultimately achieve optimal policies. So how can we quantify that notion that we believe one of them is slightly better than another one? Well, one way to do this is to say, let's see during the learning how much reward was accumulated. Let's have this thing run, let's say, for 10 million steps, and see over the entire duration how much reward was accumulated. Not just how good it is at the end, but in the entire process. So then all of a sudden you're measuring how fast the learning is, not just how good the learning is when it's done. So regret measures the difference in that sense. If you had an optimal learner that learned as quickly as possible versus your learner, what's the difference? And so random exploration will have much higher regret than a exploration function-based learner. Now, you're never going to have zero regret, by the way, in reinforcement learning, because if you don't know how the world works, you still have to try things out and find out whether they're good or bad. But different approaches will have less regret if they're better. Okay, so far we've looked at exact methods. That is, methods that give us the exact solution we need if we run it long enough. Now we're going to look at ways of approximating the solution. It's the first type of approximation we'll do, and we'll see a lot more approximation in the later halves of the course. But we'll see already one pretty basic machine learning idea today. So, what we're interested in is generalizing across states. When we look at basic Q-learning, it's nice. It keeps track of a table of all Q values. And that's good if you can fit all your Q values in a small table. But in realistic situations, the number of states to visit is very, very large. And you will not be able to store a table with a Q value for every state action pair. So if you can't do that, how are you going to run Q-learning? Maybe you say I just buy a bigger computer to store everything, but let's say that even that will not do the job for you. The space is too large. You cannot store a Q value for every state action pair. Okay, well, the key idea is going to be that we want to generalize. We want to learn about a small number of training states from experience, and then generalize that experience to do well in new situations we've not been in before, but that are related. Simple example would be, maybe you've never been in some new building before, you've been in other buildings, and from having been in other buildings, you know that trying a door is a good idea to try to get into a building. Even though you never tried that door before, you never been in that specific state before, you knew it from other experience. Can we get the same thing here? So you don't need to relearn everything in a new state, especially not if it's related to things you've seen in the past. Let's take a look at Pac-Man in action. So first, we will look at Pac-Man running Q-learning in a very small world, and we'll just see Pac-Man learning from scratch. A lot of losses, because initially the Q values aren't all that good. In fact, mostly losses. But sometimes they win, get some better reward, and might learn from that how to do better in the future, but doesn't learn too quickly. Okay, this is taking a long time. Often in Q-learning, you don't want to watch everything in detail. Let me try to close this. Let's now have it silently train for 2,000 episodes, and then after that, we'll watch it again. So it's trained silently, or it is training silently for 2,000 episodes. It's becoming better, and now it actually has a Q function that prescribes a pretty good policy, and it seems to usually win. So this took about 2,000 episodes. It's actually a very small world. There's only 6 positions for Pac-Man, 6 positions for the ghost, there's 1 food palette, but it took 2,000 episodes to learn. Very long time. Let's look at a slightly bigger one. Let's look at, still very small, but just slightly bigger. Okay, well, North action was interesting to try at first. Here's trying some other things. You look at it, it seems like it's pretty dumb. Why is it not doing the right thing? Well, actually, it's in new states. Experiencing things it's never experienced before. To us, they look similar, because being eaten by the ghost, it doesn't matter which square you're on, you're eaten. But for Pac-Man, being eaten at square 2, might be very different from being eaten at square 2, because it's a different state, and so it needs to learn a different value for that if you run standard Q-Learning. And so we want to get away from that. We don't want to have to relearn that by getting eaten by a ghost, what that means in every single square. Same thing for eating a food pellet and so forth. We want to somehow generalize experience. And that should lead to much faster learning. Okay, so to make this even more explicit, imagine you run Q-Learning and you have discovered that this state is a bad state. Well, seems a good thing to have learned. Now, what if you're in this state? That's almost the same state. But actually, it's just a different entry in the Q table, and it doesn't, if you do standard Q-Learning, you know nothing about this. How about this one? I mean, this is extremely similar to that first one. Spot the differences up here. Small difference, one food pellet is not there, but in the Q table is just a different entry, and you have learned nothing about that new entry from your past experience if you use regular tabular Q-Learning. Okay, we've seen those in action. So what can we do? You've actually seen this before in lecture 5, I believe. Let's see, games. Lecture 7. Lecture 7 in games, we looked at evaluation functions. Evaluation functions was this thing where you said, to decide how good a situation is, I can't run all the way till the end of the game to evaluate it, because the minimax calculation is just too much. What I'm going to do is just have an estimate. And that estimate is some weighted sum of different contributing factors. So, for example, distance to closest ghost. That might be important in evaluating how good your current situation is. Distance to closest dot. Number of ghosts. Maybe 1 over the distance to dot squared. Is Pac-Man in a tunnel or not? If you're in a tunnel, you might get cornered more easily, so maybe that's not as good a place to be. And many more. And so, what you do there is, you design a set of features. And these features evaluate some aspects of the current situation that you think contribute to how good that situation is. And then actually in your project 2, you played with those features and how to sum them together in a weighted fashion that this might come out well. What we're going to get new now in Q-Learning is that we'll learn how to combine these features in the right way. So, more concretely, we could either do this for value learning or for Q-Learning. Let's focus on the Q-Learning one. We'll now say our Q function is a weighted sum of feature values. And the weights here, rather than setting them by hand and us saying, oh, I think distance to ghost is so much more important than distance to food pellet, maybe 10 here, 1 there. Rather than doing that, we're going to run Q-Learning, and we're going to expect from Q-Learning to learn these weights, such that once you've learned them, these Q values computed using those weights are hopefully fairly precise Q values. Will they be perfect? Probably not, because it's unlikely that with your weighted sum of features that you can represent the exact optimal Q function. But hopefully you can get pretty close with your weighted sum of features and learn something that's very useful as a consequence to act in a new environment. And also, you can learn a lot more quickly, because thanks to these features, if you're in new states where similar features trigger, you already know something about those states before you've ever been there. Disadvantage to keep in mind is that if you don't have enough features, it could be that 2 states, as far as the features are concerned, are identical. And that means you cannot distinguish them anymore with your Q function. So you look at your features, and if you find 2 states that you think are really, really different, and one is really good, the other one's really bad, but they have the exact same feature values, there's no way your Q-Learning agent, your approximate Q-Learning agent, can distinguish them anymore, because the only thing it can do is interpret the state through the feature values. Okay, let's see. Actually, let's take our small break here and then look at how this works after the break. All right. Any questions about the first half of lecture? Yes. So the question is, why do we use this specific form factor to approximate our Q values? There are many choices that can be made there. One nice thing about having a linear combination of features is that the learning updates we'll see are simpler to understand. There are ways to make this nonlinear, and we will look at that at the very end of the course. But for now, we're going to assume that we have a set of features and that the Q function that we want to fit is a weighted combination of those features. But yeah, we'll revisit that assumption maybe in lecture 20 or something, or 22. Okay, so we want to do approximate Q-learning now. So we want to learn these weights from experiences. Okay, let's take a look at how this works. We have a transition, and based on this transition, we want to get a better estimate of these weights. Well, just like before, we can look at the difference between the sample estimate of the Q function for state S and action A with our current approximation so far. So this is the current sample, and this is the approximation so far. Then, in traditional Q-learning, what we would do is we would say, okay, we have our estimate, and we're going to correct it by some scale factor alpha times the difference, and nudge it in the direction of the sample we just saw effectively, but not necessarily all the way there. That's why alpha is going to be smaller than 1, because it's just a sample, and we need to average many samples to know what it really should be, so we just nudge it in that direction. But now we don't have a table in which to store such updates. We can definitely retrieve QSA for the state action that we just experienced. We just need to run this evaluation here, weighted sum of the features for that state action pair, but we don't have a table to store this update into. And we also don't want to have such a table. We want to instead update the weights rather than a table with Q values. Turns out that this is the update you end up with in case you want to update the weights. It's not derived on this slide. We'll see some intuition behind the derivation on some later slides. But for now, let's interpret this update. What is this saying? It's saying that the weight for feature I is whatever the weight for feature I was, plus some learning rate times the difference times the feature value. Let's think about this. Let's say the difference is positive. Okay? And for now, let's assume that the feature values are either 0 or 1. Okay? Then if the feature value is 0, nothing changes to the weights. So this was a state action pair where the feature value was 0, it was not active, and nothing changes about the weight because it's a state where that feature isn't present. Now, what if the feature value is 1? What happens? Well, the feature value is 1, and the difference is positive, meaning that the sample was higher than our estimate that we have. Then we get a positive update on the weight. What's the result of that? We make the weight more positive. That more positive weight would get multiplied with this feature value, which is 1 in our current assumption, which would increase the Q value at state SA. So we see we have the right behavior in terms of direction that it goes. When feature value is 1, difference is positive, weight goes up, which results in our Q estimate also going up, which is what we want. Gets nudged in the right direction. Now, what if the difference is negative, meaning that the experience we got through the sample was lower than we had anticipated based on our current Q function approximation? Well, then the weight will be nudged down. And that's also what we want, because if the weight gets nudged down, then that means if we reevaluate the Q value for SA, it's now going to be lower than it was before, because a lower weight was multiplied with 1, resulting in a lower sum of these weighted features. Okay, so for the 0-1 case, we get a behavior that makes a lot of sense. Now, to generalize this interpretation, imagine you have a feature that is more continuous in range. Maybe it can go from -10 to +10. Then what's going to happen? Let's first think about it being +10, so as high as it can possibly get. And let's say our experience is such that the difference is positive. We got more than we expected from our sample. Well, if our feature value is 10, very high, and we got a positive difference here, then the weight will go up. If another feature was only 1, the difference is still the same, it's positive, then it'll go up that weight by only 1. So what we see here is that if your feature was more active, the weight will go up by more. So whenever something's very active, there'll be a big correction. How big depends, of course, on the difference, and in which direction depends on the difference. If the difference is positively a correction in the positive direction, the difference is negative in the negative direction. But we see that the correction is scaled by how big our feature was. And that makes sense. Like if a feature takes on a high value, it's a feature that's dominating how we think about that particular state. And so if there's a correction to be made for that state, the weights associated with those features should be updated the most. Whereas if a feature is very close to 0, then that feature doesn't play much of a role in that state. And so when we do an update, even when the difference might be relatively high, it gets multiplied with this low number, and it won't update very much for those weights. Okay, so now we know how to interpret this, and if things are negative, then things will work out too, and there'll be double negatives that cancel out the right way. So, what's happening underneath is weights get adjusted, and more adjustment when there's a bigger difference, and when your features take on bigger values in absolute sense. Okay, let's we'll see a formal verification in a couple slides, but let's first take a look at this in action. Imagine you are in a Pac-Man world and you have two features, one related to distance to the closest dot and another one related to distance to the ghost, closest ghost maybe. And so maybe you initialize this, you say, well, I think being close to a ghost is not good, so maybe I should have something where somehow it contributes in the opposite way, where distance is actually good. So this is actually not a good initialization. We wouldn't like this. -1, you really would want ghosts to be far away, so large distance should be positive, but this is just how you initialized it. Okay, let's see what happens. We have a world, we have a current experience. We take the action north. We get from that a next state and a reward. It was a pretty bad action. We got eaten by the ghost. Reward is -500, and the Q value of S prime, there's only no actions available, the game's over, is 0. No reward anymore when the game is over. Okay, so that gives us a sample estimate. Our sample estimate is -500. What was our actual estimate? Well, that's based on this equation over here. It's 4 times F dot, which is 0.5, so that contributes 2 here. And then -1 times 1, which is a -1. Sum that together gives us +1. So our estimate used to be +1 for the state action pair. Our sample says -500. So we need to revise this down. What will the update do? It will say, okay, for each weight, we update it by a little nudge in the direction. The difference says in which direction, and then multiply it with the feature vector. And so here, for the first one, the feature value was 0.5, second one, 1. After the update, we get this approximation for our Q value. Of course, just one update is not enough. We'll need to keep doing this to get better Q values over time. But that's mechanically what happens underneath. Now let's justify this. So actually, let's watch it in action first before we justify it. We'll run Approximate Q-Learning in a pretty big grid. No success in the first one. Didn't realize the ghosts are bad, but now it's done an update and hopefully it realizes being close to ghosts is bad, but it still didn't anticipate it well enough. Definitely knows food pallets are good. There's a lot of reward in those. It now seems to have learned that staying away from ghosts is a good thing. It hasn't explored the power pallets, so it doesn't know anything about those. It's possible that the random initialization of the weights in front of the power pellet feature made it a negative thing, and so maybe that's why it's staying away from it if we don't explore enough. We see that actually this is all the episodes it's had, about 10 episodes so far maybe, and it's already playing pretty well. Compare this with the really tiny worlds where we needed hundreds if not thousands of episodes before it learned anything when using tabular Q-Learning. Why can it learn so quickly here? It's approximate Q-Learning with a small number of features. It's not much to be learned. If your features are just how close are you to the next food pellet and how close are you to a ghost, then there's only two numbers to be learned. It's how to trade those off. Once you learn those numbers, you're good to go. And that's why from a relatively small amount of experience, it's possible to learn a Q function that's pretty good. So how do we justify this a little more formally? So we'll refer to something called least squares here. Hopefully many of you have seen that before. The notion in least squares is that you have a bunch of points and you'd like to fit a line through those points, at least in the simplest version of least squares. So how does that work? So we have a feature value, f1, just one feature. We have a y, the value we want to predict. And we have a bunch of red dots which shows experiences, samples, of what we should have predicted for those specific feature values. And the way we're going to predict in the future is by fitting a line to those points. We're going to say, well, I'm going to predict it as some offset plus a slope times feature value. And one line is shown there. The question is, what would be a good line to choose? You'd probably say a line that's close to all the points. But what does it mean to be close to all the points? What does that mean? Like, how do we know which W0, W1 make this line closest to all the points? Can we make this mathematically formal? Just like, then ideally our Q values would be mathematically in some formal way close to the optimal Q values. Okay, and also you can do this in higher dimensions, of course. When we estimate Q values, it's not going to be just one feature, it's going to be many, many features. Now there's two features here, but in practice it might be 3, 4, even hundreds or thousands of features. Generalization for two features then would be fitting a plane through a set of points in a three-dimensional space, and then beyond that we can't visualize it. Actually, one thing I want to note, on the slides when we have one of these, it means that this is something we think is really useful for you to know, but that we're not going to quiz you on an exam. That's what the star means here. So it's really good for you to know this, but we also know that we don't require maybe in our prereqs the background that makes this maximally easy to follow along. And some of you might not have that background, and so we're not going to require you to now go study that background to understand these few slides. But we think most of you do have the background and will benefit a lot from seeing where this comes from. So least squares, what does it do? It says I'm going to measure vertical distance of my line to each of the points. And I want the sum of the squares of the vertical distances to be as small as possible. That's how I'm going to measure how good my line is. So that would be this. yi hat is my prediction. There is yi, which is given. And then I want to see the difference squared, y squared, because if we just average the differences, that's not a good measure, because then positives and negatives will cancel out. We need to make sure the positive and negative errors don't cancel out, because both positive and negative errors are bad. So we square them, sum it all together, and that's our objective. Our predictions are in the form of a weighted sum of feature values, so that's what it looks like. So what we really want to find then is a set of weights, W, 1, 2, 3, and so forth, such that this thing is minimized. In principle, you could try all possible settings of weights, see which one achieves the lowest, and that's the one you want. But these are continuous variables, so trying all possible settings of the weights is not practical. There's infinitely many choices. So we need a better way to find the best setting of the weights. So what we're going to do is something a lot like the local search you've seen in the CSP lectures. So let's say we had just one point, one term in that objective. And this will generalize to if we had many points. And we have this thing over here. Can we do something closer to local search? What did we do in local search? We had a current choice of our variables. In this case, our variables are W, 0, 1, 2, and so forth. And can we maybe change that choice to make it better? And then repeat, 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 and hopefully we end up at something good. Can we do the same thing here? Well, the question is, can we do something maybe even smarter? Instead of just changing it and hope that it might get better, and otherwise revert it, can we know in which direction we should change each weight? Should weight 1 go up or down? If we can decide that, then we can, in a much more informed way, get to a good low error. How do we know whether we should move a weight up or down? Well, we should say, well, if we change the weight up or down, does the error go up or down? And we want the error to go down and nudge the weight in the according direction. Mathematically, what that means is we compute a derivative. So you would say, what is my error, which is my function I'm trying to minimize, as a function of Wm, one of the weights, and I want to see the slope. I want to say, if I change Wm, how much does my error go up or down? That's what this thing is saying. It's saying, if I change Wm and I do +1 for Wm, then this is how much my error will change. Okay, if we can do that, then we can do an update to the weights. We can say, okay, well, if the slope is 0, no update needs to happen because that weight does not affect the error. But if the slope is non-zero, let's say the slope is, let's say this is a positive slope. If I make Wm go up, the error will go up. Then I just step in the opposite direction, step in the negative direction, and that's exactly what's happening here. There's a negative sign. That negative sign has disappeared. We step in the opposite direction of the slope because we want to go downhill. So that's our update here for least squares for that weight. We can do that for all weights, and that's exactly what's happening in the Q-Learning just as well. In Q-Learning, we formulate an error function, a squared error function for the current sample. What is our sample estimate? What is our Q function? We can look at the squared error, take the derivative with respect to a weight, and then based on that derivative, that will be this thing corresponding to this thing over here. This here corresponds to this over here. And that tells us in which direction to step, and then we'll step scaled by alpha. We didn't fully derive this on the slides. This is just meant to give you some intuition behind why what we're doing in Approximate Q-Learning is actually well justified. Any questions about this? Yes? Okay, question was about the negative. So let's look at this again. So what we're trying to do, we're trying to make the error as a function of our weights as small as possible. What this derivative is saying, it's saying if I change Wm by increasing it by 1 unit, how much will my error go up? But I want to move in the direction where the error goes down. So this quantity here will be positive if moving W up makes the error go up. But if that's the case, we actually want to move in the negative direction. And so that's why the negative that ends up, if we take derivative, we end up with a negative over here. That negative disappears when we look at the update, because we want to move in the opposite direction of the up direction on the error. Okay? One thing to think about, and we'll look at this more in the machine learning at the end of the course, is that you don't necessarily want the more features, the better. You can have too many features if you have a finite amount of data. For example, imagine you are fitting a function to this set of points. You might say, well, let's fit a line. And say, okay, that's my line. Maybe it's even, you find the least squares error line, and you're like, okay, but it's still a bunch of error. So you might then say, well, not so much a fan of a line. How about a parabola? Parabola, okay, let's fit a parabola. Maybe now you're a little happier. What does it mean to fit a line? A line means that you say y is w0 plus w1, oops, what's that? w1x. A parabola means that you say y is w0 plus w1x plus w2x squared. If you want a third order polynomial, same thing, plus w3x3. So, as we want a higher order polynomial, what that means is we introduce more features. A new power of x is a new feature. And so, as you introduce more features, you can start fitting this more and more closely because you have more flexibility. the set of functions you represent by a third-order polynomial is strictly more than you can represent by a first-order polynomial. Because in fact, they're all included in the third-order polynomial by just setting some coefficient equal to 0, but you can set those coefficients to non-zero, expanding the things you can represent. So you might wonder, well, what if we fit, let's say, a 15th-order polynomial to this? Wouldn't that be nice? Well, maybe, but this is what you get. What you see here is that if you just look at the points that we're trying to fit, it does really well, but then some other places, it does something that we likely don't want it to do. That's called overfitting. It's trying to get all the points correct, but as a consequence, it ends up doing some crazy things in other places. And so in practice, and we'll see a lot about this in the late lectures, you need to guard against this kind of overfitting. For now, the best way to think of it is that you don't always want just more and more features, because you'll have these weird things come up, and then crazy things happen, and you might as well have anybody draw some line through the points and call it done. Okay, so that's Q-learning. Now, we're going to see a different approach to learning good policies to act in worlds. So we've seen value learning, we've seen Q-learning, now we're going to see policy search. In policy search, you kind of just say, hey, there's many policies to choose from. Ultimately, I want to end up with a policy. Let's forget about learning Q values, V values. Let's just try different policies and see which one is the best. And then we call it done, because we found the best policy. Okay, so the reason you might want this is because when you have approximate Q values, even though it might work well, if they're approximate, what they're approximating is trying to get this least square error down on this Bellman equation. And we know that's related to good performance, but it's not directly tied to good performance. It's approximating something that is related to good performance. Can we do something else? Well, for example, if you look at Q values, it could be that some Q values are much better than other ones, but the way they differentiate between actions, one of them picks the right action, the other one picks the wrong action. The priority in Q-learning is learning Q values that are close, not making sure that the action that's the best is favored over the action that's not the best. Okay, so what if we directly pay attention to the actions? Policy learning. One way to do this, we could say, we start with an okay solution, so we have Q values, and then we're going to fine-tune by hill climbing on the feature weights. What does that mean? We have some Q values, and then we can nudge the feature weights up or down, see what happens, just like we did in local search for CSPs. If it's better, we keep the change. If it's worse, we discard. We discard it, and we repeat. And over time, we might find the policy that's better and better and better. Now, what does it mean if a set of weights is better or worse? Well, you need to execute the policy and see how well it does. Now, you might have to do this many, many times because the world is stochastic, and so sometimes maybe you're lucky, sometimes not. So it can be somewhat expensive, and in general, policy search tends to be less sample efficient, means you need to collect more experience to learn to do well with policy search than you need with Q-learning, but it's often a little easier to understand what's going on. You have this policy, you nudge it, if it's better, you keep it, if it's worse, you discard it, and you go again. Okay, so often people will use a combination where maybe you start Q-learning, fine-tune with policy search, and there's even other ways to combine them, which we're not going to get into here. Let's look at some example success stories. So here is a helicopter. Helicopters are very difficult to control. You might wonder why. You've flown in a plane many times, and you've heard people say, well, if the pilot goes to sleep, the plane will still fly, because even if you make a paper plane, you just throw it and it flies. It naturally flies. With a helicopter, actually, it's not like that. It's more like a rock in the sky that wants to drop, and you need to put effort into keeping it in the sky at all times. To think about it a little more carefully, what's really going on with a helicopter is closer to, let's say you have a very flat surface, maybe something like this, but a tray that you can hold, but with no boundaries to it. Just flat, and it ends at some point, but there's nothing coming up on the side. You have a marble on it, and now you need to walk somewhere, and you need to make sure this marble doesn't roll off your tray. That's effectively what pilots are doing when they're controlling helicopters. So it's really hard. If you don't adjust for what's happening right now, a wind gust that comes in or some other perturbation that comes in, then you might be on your way down. So you need to pay a lot of attention as a pilot to make sure to keep it in the air. So it's also hard to design controllers for this. But with reinforcement learning, a controller was designed for this helicopter, and let's take a look at this helicopter in action. Okay, so this is extremely stable helicopter flight. Helicopter is pretty much not moving, very hard to do even for the best human pilots. It's also upside down. So what's going on there? You might not have flown a helicopter upside down or seen it fly upside down. How come this works? Let's think about this. How do you control a helicopter? You have 4 control channels. Channel 1 is the average angle of attack of the blades. And the steeper you make that, the more air you push down, the more thrust you have. You can actually also make that negative. You make it negative, you would go down very quickly, except if you are upside down, in which case the negative angle would keep you up. It actually turns out it's more efficient to fly this way. Any thoughts why? It's definitely not more comfortable, but... Sorry, say it again? So the answer there is, the proposed answer is all the thrust that you generate is used to lift the weight of the helicopter here, whereas maybe if you fly the normal way, you're not using all the thrust. And that's the right direction, but I'm going to refine that answer just a little bit. If you think about what happens when you keep a helicopter up in the air, you're pushing air down. Force for the air down, helicopter gets a counter force to stay up. When you push that air down, it's much faster than it was before. It's going down quickly. If it's going down quickly over the body of the helicopter, it's dragging that body down. And so what you have is kind of a double effect of pushing air down. You get a counter force keeping you up, but also then you generate drag over the body of the helicopter dragging you down, or trying to drag you down. When you flip it upside down, that's not happening. There's still air coming over the body of the helicopter, but it's coming in from a wider intake, and it only goes at half the speed compared to the air that's coming out. And because drag is squared in the velocity of the air, you get 4 times less drag flying this way than flying the other way. You might wonder, how do you control this tray that you're kind of balancing your marble on? One thing is the angle of the blades. The other thing you control is differential angle of the blades throughout the cycle. So for a helicopter to move forward, you can't just ask, let's move forward. You actually have to tilt the nose down, and then the thrust will be such that some of your thrust is getting it to go forward once combined with gravity. How do you get your nose to go down? Differential amount of air pushed down, front, back, left, right, allows you to rotate the body of the helicopter. So that's the cyclic control, and so there's something in there called swash plate that ensures that you go through cycles of different angles of attack as your blades rotate at something like maybe 30 times per second. You have a fourth control, which is to make sure that is you're facing the direction you need to be facing. If you don't have the tail rotor, what will happen is your helicopter body would spin counter to your blades. But the tail rotor compensates for that by also having a differential angle of attack, and you can control that to then also decide which way you want to look. Okay, that's helicopters. You might also wonder, why don't people fly upside down? I've wondered that too. Probably it's just not that easy to build helicopters that humans sit in a way that is comfortable to fly them, yet then also sustainable flight upside down would in principle be more efficient. Here's another example. So here we're going to watch reinforcement learning in action for a legged robot. What do you expect to happen here? Well, we know how reinforcement learning works. Initially, it doesn't know what to do. It's exploring. But then hopefully over time it becomes better and better and better and figures out what it should be doing. So it's just falling over. It's falling over again. But it's falling over a little later. And it's better to fall over later than earlier. And it knows that. It's getting higher reward now. And now it's getting very high reward. Now the beauty of reinforcement learning is that you don't have to write new code for a new robot. You just swap in a new robot, run the same code, it can learn to run. Here the robot starts on the ground, has some extra learning to do. It wasn't on the ground before. It gets rewarded for getting the head as close as possible to standing head height. The closer, the better. And it figures it out. Here, two of these robots are learning together, and they're practicing soccer. One of the beauties here, aside from how they run, is that they can train each other. So they can gradually both improve in what they're able to do. As the goalie gets better, the penalty kicker needs to get better to get reward, and they can gradually get better and better together. You can do this with real robots. Let me pause this for a moment. This is Brett, the Berkeley robot for the elimination of tedious tasks. Brett lives on the 7th floor of Satarja Dai Hall, and in this video is learning to play with a children's toy. This video is sped up a little bit. This takes about 1 hour in real time. But it is reinforcement learning to do something it's never done before. You might say an hour is a long time because you could do this first time, at least I hope. You all could do this first time. But it's not really true you could do this first time. Because the first time you did this was maybe when you were 1 year old. And you might not have succeeded first time around when you're a 1 year old. And so you need to think of this reinforcement learning agent as really a 0 year old. Hasn't done anything yet, is born in this world, not having done anything, but getting rewarded for putting that red block into the matching opening. And it just goes at it till it optimizes how to get it in there. Here's another example. Let me pause this before we run this. This is NASA's Super Bowl. It's a research collaboration we've had with NASA on this robot. You might wonder, why would they make a robot this way? And especially, this one is for planetary exploration. So go visit planets that maybe humans is hard to send to, but maybe a robot can go explore for us. Well, what's beautiful about this robot is that it's a sphere in some sense. And so what you really get is wheels in every possible direction. And wheels is what you need to get places. The other thing you get is if you lengthen the cables enough, this thing can be completely flat. If it's completely flat, then it fits in a rocket very nicely. Very small volume. If you then expand it again, it can land with some damping. So you need smaller airbags this way than with a standard rover that you might land. The only tricky part now is that this is very non-intuitive to program how it should do something. But reinforcement learning was able to solve that problem. And here we have in this case, we had reinforcement learning run in a simulated environment that simulates this robot, learn in simulation after many, many trials how to control the simulated robot, and that was then deployed on the real robot, and this is tested here at NASA in Mountain View. How about a hand? We use our hands a lot. Clearly there's control involved. Can we have reinforcement learning learn to control a hand? Let's say in robotics, hands have really proven challenging. And the reason they've proven so challenging is because there's a lot of actions to be taken at any given time. There's a lot of degrees of freedom. And you need to control them all the right way to get a good outcome. Most outcomes will be bad. Most outcomes of controlling this thing will be the cube drops on the ground. And that's it. There's only a very small set of ways of controlling this that actually lead to a good result. And how do you find that and zone in on that? Here we're not going to watch the training. We're just going to watch the final capability. This was a result done at OpenAI. And what we see here at the bottom right is what it's supposed to achieve. And we see that indeed it's capable of reorienting the object it's holding to match up with what's in the bottom right. One interesting thing here is that this one also was trained only in simulation. But it turns out building simulators for something like this that are accurate is not practical. But the agent was trained in many, many, many simulators and was trained in a way that it could do well in all of these simulators. And it turned out that if it was good enough to do well in all of these simulators, even though all of them were inaccurate, something that was good for all inaccurate simulators was also good for the real world. So it's a strategy to get something to work in the real world is get it working on many, many different simulators. Go, robot. There it is. So, At this point, we're not just concluding this lecture, we're actually concluding the first stretch of the course. What we've seen in the first stretch of the course is search, CSPs, games, MDPs, and RL. That's about search and planning with a bit of learning. What we're going to see in the second part starting Tuesday is probabilistic reasoning to deal with uncertainty and a lot more learning to learn from data rather than having a simulator ahead of time available to you. Okay, that's it for today.